All right, cool. Hi, I'm Eugene Vinitsky. I'm a faculty here at in the Civil Department and also at C2 Smarter. And I'm affiliated with Computer Science Engineering and the Center for Data Science. I'm going to be talking about robust autonomy emerges from self-play, a paper that we put out on arXiv a couple months ago and is now accepted at ICML. Which I think is work I'm extremely excited about. I think it shows kind of a new way to build a particular component of a self-driving car in a very scalable, cost-efficient way. And for me, though there are multiple people on this paper, the underlying genesis for this work is that basically we know one way right now to build anything that is at expert human level. Some caveats about ChatGPT aside. Basically, the way that we know how to do that is self-play, which is a technique from multi-agent reinforcement learning. And it's kind of the pipeline that we've used to build human level or superhuman bots in StarCraft, human level Stratego, superhuman Go, superhuman chess. And I'll talk a little bit about why that is. But in short, the question that has irked me for a long time is, we do this for bots. We can build superhuman bots with these like game theoretic techniques. But this is not how we build self-driving cars. This is not how we build robots. This is like stuck in these kind of games that we used to play as children. And so trying to bridge that gap is the underlying thesis behind this work. So this talk is about how self-play RL is not just a tool for games. It is also a useful tool for building general multi-agent autonomy. And so there are going to be kind of three key results that I'm going to talk about here. The first is a simulated, potentially human-level self-driving car. So it's going to be we're going to build a simulated car that zero-shot saturates every benchmark we're aware of, and according to some measures matches human-level performance. Everything will come with caveats. Two, a simulator that we built that can generate millions of hours of driving data per hour per GPU. Three, a demonstration that a robust planner, and if you don't know what that is, we'll talk about it in a bit, for a self-driving car can be a tiny end-to-end neural network, like 3 million parameters, way smaller than anything, commercially deployed. So this talk is going to be how to build an autonomous car with no human data. So in short, to give an overview, we're going to first talk about designing end-to-end planners with minimal or no human data. I'll give you an overview of the technical approaches that we use to make this happen, and end with some observations about what happens when you scale up reinforcement learning. So the content of this talk is pulled from this paper, Robust Autonomy Emerges from Self-Play. I normally don't spend so much time on the author slide, but I do want to stop here to point out that every author here with the star was an equal contributor to this paper, so we're in alphabetical order. And so even though I'm the person who gets to talk about it, this is all our joint work. And this project was also led by Philip Cranbuel and Love and Colton, and everyone besides me is at Apple. Building a robust multi-agent planner from self-play. So to kind of give you some context here, let's think about what the self-driving stack looks like. We have some perceptual system, which either a LiDAR, camera, radar, ultrasonics on a car, and that takes the world and converts it into some perceived format, like bounding boxes of cars, where the pedestrians are, where the edges of the road are, what's drivable, what's not drivable. That then gets passed into a prediction module. This is what most self-driving car stacks look like. They don't all look exactly like this, but they mostly look like this. So it goes into a prediction stack, which then takes all those positions and converts them into predicted trajectories of everything in the scene. Those predictions are then passed to a planning module, which says, here's a bunch of trajectories that seem like good things for our car to drive along. Let's figure out how to assign some costs to them and pick out from those trajectories which of them is probably the one that we should follow. And that then goes into a control module that kind of tries to follow one of those trajectories. And this loop will run over and over somewhere between 10 and 100 hertz in most cars. And what we're going to talk about here today is a simulated end-to-end planner that plausibly subsumes this part of the stack. So directly from perception to kind of outputting control signals. So no explicit prediction, no explicit planner, just end-to-end perception to control. And we're going to do this in a fully human data-free way. So everything is going to come from simulation, which means that we don't have to go out into the world to collect expensive human data. Yeah. So there are a couple ingredients that are going to go into this. And I'm going to kind of walk you through them and then talk about the results. The first thing is we need some kind of scalable algorithm. So I'm going to give you a super fast intro to self-play, which is the underlying algorithmic technique that's used here. The idea of self-play is we have some current policy. So in this case, our like end-to-end planner is going to be represented by pi sub t. Inside Simulator, we have, you know, 1 to dozens of copies of pi sub t, and we're going to roll out trajectories from pi sub t. I'm going to take all those collected trajectories, called collected games. We're going to pass them into some kind of update process, and that's going to return us a new policy, pi sub t plus 1, that's better than pi sub t, according to some measure. So we're going to have some cost function that says how good a trajectory was, and we're going to try to return a policy, pi sub t plus 1, that improves on that cost function. Or generally, we'll say a reward function. So we're going to try to make the reward go up. Inside that box, what this looks like is from the perspective of each policy pi sub t, we are taking some action in the world. That action goes into the world, and it updates the state of the world, and it returns us what we see next, O sub t plus 1, and a reward, R sub t plus 1, that says how good that kind of state that we're in is. And we're just going to run that loop over and over again from the perspective of each policy. And, you know, kind of just to highlight what this looks like, you know, here we have a scene in a simulator. We have a bunch of cars driving around. Each of them wants to get to their goal, where the goal is colored by their respective color. And every agent in this scene is a copy of pi sub t. So they're all driving the same policy locally, but it's fully decentralized, right? So they're all making their decisions totally independently, but with the same neural network running on board every car. And so in a given rollout, we'll collect trajectories from however many cars are in this scene. And in our particular case, those collected trajectories are going to go into an algorithm called proximal policy optimization, or PPO, and that's going to convert those trajectories into an updated policy. And the reason I'm not going to focus on that is that I don't think it's super important. This is just like the black box algorithm that we use that gives us updates. Caveat, it is kind of important. I do think you probably have to use this class of algorithms, but like we don't do anything. This is the vanilla version of this algorithm. So we're not doing anything super special there. And to revisit, this kind of self-play loop is basically how all human level bots are built. So, you know, it's the underlying thing behind StarCraft, behind Stratego, behind Go. Though each of them use a different algorithm than the one that we're using here. And we have some work in a lot of different settings suggesting that these type of policy gradient methods or proximal policy optimization methods are actually good, plausibly general purpose solvers for multi-agent games. So just a good class of algorithms. Okay. So why don't we just build cars this way? Why don't we just like set up a simulator, run things around in it, do some optimization, and at the end we get something that looks like a good self-driving car? And the distinction between these type of zero-sum games, like Go and chess and poker and all that, and self-driving is there's a lot. So the first is, you know, when we think of the games that we've managed to build superhuman bots in, they're all this class of games called zero-sum games, and particularly two-player zero-sum games. So games where somebody wins and somebody loses. And there's two players, one wins, one loses. So you could think of poker as an example of this. And there are two properties of these games that are really helpful. One, we have a known reward. It is very clear what it means to win the game, right? Two, specifically for two-player zero-sum games, there is a best way to play. It doesn't matter who your opponent is. There is a well-defined notion of what it means to play well. And when we move to the driving case, we lose all of that. First of all, we have no idea what the reward function is. Like how do I write down a cost function that says this is good driving? I mean, people do try to do this. If you go to a self-driving car company, they will have some cost function that for a trajectory evaluates it and says, this was a good trajectory. They'll have something like that. But you have to think about what that is, and you have to write it down and be careful about getting all the terms in there correct and so on, or maybe you learn it from data or something like that. B, the best way to play is context dependent, right? If I am a car and I drive on the right-hand side of the road, that is not the right way to drive in Singapore, which is a left-hand sided driving thing, right? So there isn't a unique best way to play like there is in poker. It depends what the other drivers around you are doing. So in particular, it means that you have to drive in a way that is kind of how humans around you expect you to drive. So the way that companies increasingly resolve this right now, and an increasingly popular approach, even at companies like Waymo, and not that I have any insider insight, I just you can kind of infer from the papers they write and what they say, is to solve this problem of there being uncertainty about what the right way to play is by collecting a lot of human data. So if you're a company like Tesla, you have roughly like billions and billions of miles of humans driving around. You have the steering actions that they took while they were driving, and you can store what the cameras are seeing, the steering actions that they were taken, and fit this into a supervised machine learning pipeline and just say, for this state, map it to that action. And the idea is you're going to take those like billions of miles, you're going to combine it with some big ML model, and as you scale up the amount of data, you're going to get something that looks more and more robust over time that kind of matches human driving. And this does kind of work. You know, Tesla is now somewhere between 500 and 5,000 miles per disengagement, somewhere in that range, which is really impressive. But you know, you really need to get somewhere between 100,000, sort of order of 100,000 miles per disengage to like really let somebody take their hands off the wheel. And honestly, way more than that, more like millions of miles. So what we'd like to do, you know, because we're not all Tesla and we don't all have billions of miles coming into our cars, into our data centers every day, is figure out something that doesn't go through human data as this fundamental bottleneck. Maybe it uses a little bit of human data, but some way that we could get rid of this bottleneck. So we'd like, or I would like, and we do in this paper, some kind of cheap, diverse simulation that we generate millions of miles of simulated data from. We would also probably like cheap, tiny models because running inference on these big neural networks is really unpleasant. And out of that, we would like to come something that looks like superhuman robustness. So hopefully this video plays, but you know, something that, you know, you could maybe see it like really good at dodging collisions, you know, doesn't ever collide. So the question underlying this work is how can we get away from human data and instead scale with simulation? And there's a few ideas that are key here that we're going to take advantage of. The first is we're going to try to make train harder than test. We're going to build a really complicated simulator that is unbelievably unpleasant to drive in. And then when you want to deploy the system trained in that simulator into the world is easier than that simulator, right? So we're going to build a simulator and we're going to fill it with cars that drive in the wrong lane and cars that are kind of pushy and cars that wait too long at a stop sign and cars that drive through red lights. And the policy that kind of is ready for all these things is definitely ready for nominal driving, just like, you know, driving straight along on the highway. And so even if in our simulator, we only have synthetic drivers and no human drivers, when we do start playing with like human policies, they're kind of easier to play with. The second idea is that when we spin up this gigantic synthetic simulated world, if we do it right, we're going to learn a lot of basic skills just from interacting with the agents in that world, right? So like, I just have 3 examples here that I think are kind of useful and we'll kind of reuse some of the notation. So agents want to drive to these little green pins. So somewhere it has a goal. Agents would like to get to their goals and the goal is somewhere off the map. And our agent, which is the blue agent, you know, initially is just driving straight along towards its goal. But it doesn't know anything about this orange car. It doesn't know if that orange car is paying attention, right? And so as it's driving, it has to be cognizant of the fact that at any point, the orange car could decide to swerve into its lane for no good reason, and it's going to need to be able to swerve out of its lane. And so when you drive around millions of these miles with these cars and you're kind of like uncertain over their trajectories, you kind of learn to be ready for a swerve. This uncertainty over goals kind of builds something really fundamental into the policy. So here again, we're the blue car. We're trying to get to this green goal that's at the bottom of the map. And there's another orange car that's driving along. And while we would like to make this left turn, we don't know whether this orange car is going to yield to us or not, right? And so we have to drive in such a way that if it yields, we can keep going through. And if it does not, we are ready to brake, right? So this is sometimes called like contingency planning. And if you have enough uncertainty over the goals of other agents in your simulator, you're going to kind of build this into the agent. 3, you kind of need to learn to reason about risk, right? So like things that might happen in the simulator, for example, is this orange car here is going to come to a stop. And we'd like to get to our goal that's all the way out there on the other side of the map. And to do that, we're going to need to go into the other lane, right? Which requires reasoning about, is this car stopped? Is it likely that a car is going to come around the bend and hit us even though we're in the right lane? Do we have enough time to like make that maneuver, even if we were wrong about that and a car does shoot through on the wrong side of the lane? So if you're really good at driving this world, you're going to need to be really good about reasoning about risk. And these two things, this like uncertainty of the simulator and the diversity of the simulator, are kind of knobs that you can use to control the amount of robustness that you push into your car, right? If you set uncertainty and diversity to the max, you will never go out onto the road. There's no reason to drive. It's way too scary. But you can kind of tune and play with these and control how robust and risk avoidant your policy is. And then ingredient 3 that we're going to use is 1 trillion steps of agent experience, which is 1.6 billion kilometers of driving. So putting this all together, we've built a system that we call Gigaflow. Gigaflow is a fully vectorized simulator. So it's written entirely in PyTorch. And basically we have a node of 8 GPUs. On every GPU, we place 8 copies of 4,800 copies of one of these 8 maps. These 8 maps are taken from Carla. It's like a standard driving simulator that people use. They vary a lot in size. Some of them are a few hundred meters in any given direction. By the way, if you have questions, please interrupt me. This talk can be arbitrarily long or arbitrarily short. Great.
About the previous section, is the reward include does it include the speed as well? Because I think if it's over cautious, then it's going to be slow.
Yeah. I will get to the reward in a little bit. There's a very particular reward design that we adopt here that's very important. It's a good question, but I will get there. Any other questions? Okay, so we have 4,800 copies of this map, and writing the simulator is very tricky, right? Because you have 40 gigabytes of memory on these A100 GPUs, and you need to fit 4,800 copies of this map on them, plus all the agents that are on them, plus all the rollouts that they generate, yada, yada, yada. And some of these maps are quite large, they can be like kilometers in any direction, but they roughly cover the set of things that you might experience in the world. They have roundabouts, they have on-ramps, they have clover leaves, they have things like this. And what we do is in every map, we place up to 150 agents in the map, and we scatter goals randomly throughout the map. So every agent will have between 1 and 3 goals that it knows it would like to reach. And it's rewarded for reaching those goals without colliding while driving in a particular way. And I'll talk about the details of that reward function. But at the basic level, the thing to understand is that agents would like to get to their goals without colliding. And they know where they are. They have a rough route that tells them how to get to their goal that they do not have to follow. They can follow that route if they want, but they don't have to. And these goals are scattered all over the place. And sometimes to get to your goal, you have to drive in the wrong lane. Sometimes to get to your goal, you have to do a U-turn. Anytime 2 cars collide, they come to a full stop. And so also sometimes navigating around this map means like some roads will be impassable. And so altogether, on every GPU, we'll have millions of agents running around. In total, running the whole training loop will run at about 100,000 steps of agent experience per second.
Quick question.
Yes.
Proportions of policy agents versus those hard, like driving like
They're all policy agents.
Okay.
Every single agent here is a policy agent, but we're going to make them act differently using a little trick that touches the reward function. But every agent here is a copy of the same policy. And that's really important because that's actually what lets us run this so fast. Looking at it from the perspective of the agents are all very different. Some of them are big trucks, some of them are thin little bicycles, some of them are tiny little pedestrians that are allowed to cross the road edge, but they're all controlled by the same policy. And the way that we make that work, and also this is kind of what they see. They see the cars around them, they see the road as kind of dotted lines, they kind of know where their goal is, and they kind of know where the centers of the lanes are. Basically, each of these policies take as input the boundary of the road, the lane points, a stop line, which is a traffic light. They know something about their own state, how fast they're going, what their heading is relative to the lane. They see the other agents around them. And then they're also conditioned on their size. So they know how big they are. And they also know that their dynamics are a function of their size. So if you're a very small pedestrian, you're very maneuverable, you can turn very fast. If you're a big truck, you can't turn very fast. But so the agent knows what type of car it is. In total, the system generates over the course of 10 days, the equivalent of 10,000 years of driving experience. We simulate millions of drivers at a time. In total, we train on 1.6 billion kilometers of simulated driving, which takes somewhere between $2,000 and $7,000 to train on the 8 GPU node that we did, which is a lot of money. But on the other hand, I also think it's not that much money. So, depends who you are. But the other way I like to think about this is $5 per million kilometers of driving. So, if you want to get kind of statistical guarantees about what's going to happen over 1 million kilometers of driving, it'll cost you $5. 1.6 billion kilometers is the distance between the sun and Saturn. And on this graph, kind of rescaled, we have the size of the available open source data sets that are online. So, they're all between 0.05 million kilometers. So we are, roughly 100,000, 20,000 times bigger than the total amount of human data that's available online. Now that human data is valuable in other ways, but it's just kind of get across the scale. So to Farnoosh's point, one thing that we do to generate the diversity that I was talking about is we do this thing that we call randomized reward conditioning. So we have a cost function that consists of multiple terms. The terms consist of desire to get to your goal, but also how much do you care about being centered in your lane? How much do you care about getting to your goal quickly? How much do you care about being aligned with your lane? How much do you care about jerky actions, like turning your steering wheel very sharply? How much do you care about your velocity being aligned with your lane? And each of those reward terms has a different weight in front of it, a different alpha value. So we weight all those components differently. And we basically sample those components from a different distribution from each one and provide those weights to the agent. So every agent is optimizing a different reward function at any given time, and it knows what reward function it's optimizing, and it changes its behavior in response to those weights. So for example, if we switch the center bias from being low value to high value, the agent will start driving in different lanes. And if you make it negative, you can actually make it drive in the opposing lane instead of it's the correct lane. Or if you play with this goal value, it will take riskier actions to get to its goal sooner. And so this creates this really rich, diverse world full of agents that both obey the rules, but disobey the rules, act risky, don't act risky. And you know which one you are, but you don't know which one everyone else is. So, yes. Yeah.
So through the course of the simulation, the weights for a particular agent are fixed, or you change those as well?
Every time we rebuild the world, we resample. But over the course of a single life for an agent, it's fixed. We also, because the agents are randomized, you can make them behave, because they have different goals, you can make them take different trajectories by moving their goals around. So these are different trajectories that the agents take depending on what their goal is. And they also take very different trajectories depending on their size. So here's an example where we have an obstacle and we change the size of the agents in 3 ways. When it's this thin, its goal is out over here past the obstacle. And the shortest way to get to the goal is to drive through the obstacle. When it's this thin green car, it knows that it can fit through the obstacle, so it takes the route and it takes the shortest route and goes around the obstacle. When it is this big truck, it knows that it can't fit the obstacle, so it takes a longer route to get to the goal. But because it's a big truck, it does a 3-point turn to turn around. But when it's this much smaller, more maneuverable car, it just does a quick U-turn and goes around through it. So we also have this additional aspect of diversity in our world. Okay, we put this all together. We train for 1.6 billion kilometers, 10 days on an 8 GPU node. What do we get out of that? Why is all this effort worth it? Well, the policies that come out of Gigaflow are the first policies we've ever seen that are state of the art on every benchmark we tested them on, despite never training on that benchmark in any way, shape, or form. We don't use any data from that benchmark. We don't do hyperparameters on that benchmark. We just immediately deploy the policy to the benchmark, and it works really well. It's actually state of the art in all the ones we tested. I mean, this was in 2023, so the benchmarks have changed a little bit, but at the time. There are 3 benchmarks we test on. The first is Carla. Carla is this like photorealistic simulator that a lot of people use. And in it, we test on a benchmark that consists of between 1 and 20-minute long drives. But the really interesting thing about those drives is all the policies beside ourselves in this benchmark consist of these hand-designed policies that somebody has written down and programmed up, right? So they are not policies we've seen before. They're these weird synthetic policies that behave in very strange ways. But despite that, this dotted line is a prior state of the art, and we are well above state of the art. And to the point where basically we think that almost every ding that we get that prevents us from getting a score of 100 is a fault of the benchmark. Like sometimes like you'll be driving and a pedestrian runs into the side of your car. And there's really not a lot you can do about these like death-seeking pedestrians. But we really don't think you should lose points for that. The other benchmark, which is very out of distribution, is New Plan. So New Plan consists of drives in Boston, Vegas, Singapore, and some other cities. And the out of distribution thing here with respect to the behavior is that these are New Plan replays log trajectories of human data. So we take trajectories that humans actually drove. We replace one of the cars with our car, and we ask it to drive smoothly without colliding with those cars. And so these are actual human replay trajectories, again, a thing we've never seen before. And there, we outperform the state of the arts, 0 shots. One caveat is, for similar benchmark flaws, you really can't get 100% here. And also, there's some specific things we could do to push up the score a little bit more, but we didn't want to tune the score per benchmark. And then the third, again, this is sort of a benchmark that we created ourselves because we were running out of benchmarks to try. Is something vaguely built upon Waymax. So Waymax is or the Waymo open motion dataset is a dataset from Waymo, consisting of human drives in mostly San Francisco, Phoenix, Los Angeles, maybe. Yes?
I'm sorry, what is the score exactly representing?
It's each of these benchmarks have their own scoring system. It'll be some mix of like drive smoothly, get to your goal, don't collide, kind of behave the way we would expect a human driver to behave. They each have their own totally separate scoring function. They're all kind of getting at the same idea, but they're each, it would take a long time to go into the details of what each term in there is. They're called driver scores, and they're intended to be measures of good driving. Occasionally they deviate. For example, in Carla, like you have to occasionally drive through red lights to optimize your driver score. So, they're not perfect. And here we're mostly talking about getting to your goal without colliding. And unfortunately, Apple has not authorized the release of the videos, but when we do collide, it's usually the other cars doing something extremely weird, like driving through 3 cars and then smashing into us. Not really. So we do well on synthetic benchmarks. We do well on benchmarks that consist of replayed human data. And this is all stuff that we've never seen before, which I think is pretty exciting. And down here at the bottom, we have kind of plotted where we hit the prior best scores in our 1,000,000 kilometers and when we plateau and our score stops improving. So we kind of do need all this 1,600 kilometers to match these scores, but we're getting something for it. Unfortunately, yeah, I would love to show the videos of all the failures because they're extremely enlightening, but not authorized for release yet. The other cool thing is we can construct out of distribution scenarios and see, or scenarios that are plausibly out of distribution and see that the car learns to solve them. Again, there's a really cool video here that I wish I could show. So here's a scenario set where we place a bunch of cars behind this obstacle on a freeway. So we can imagine that, you know, some pileup has happened and every car needs to route itself around that pileup to get through. And at the beginning of training, we're going to color cars by orange based on the probability of colliding during trying to get through, and green for getting through. And at 100 million kilometers, almost every car collides. At 1 billion, it starts to get better and better. And at 10 billion steps of training, 10 to the 11 steps of training, all the cars kind of smoothly route around each other to get through. Like you'll see that they pile up right here, and then they kind of jostle to see who is allowed through, and then they go through, and sometimes they'll even back up a little bit to let somebody else jostle through, and it's really beautiful to watch and very human-like. We also see that the Gigaflow policies learn long horizon decision-making. So long horizon decision-making is something that's really hard to do because when you have a conventional planning method, you plan over some finite horizon, and it's unclear what to do at the end of that horizon. So what we have here is a scenario where we have a goal over here. There is an obstruction that is going to prevent us from driving through to get to that goal. And what we see is that if we use a kind of short horizon planning method, it starts to drive towards that obstruction, realizes it's a bad idea once that obstruction is within its horizon, and then turns around and starts to go the other way. What we see is that if we look at the value function of our policy, which kind of scores how valuable a state is, it says that being near that obstacle is extremely bad. So our value function knows that it's bad to be near there. And our policy, what we see is it immediately reroutes itself. Rather than take this shorter route to the goal, it takes the longer route around to get to its goal. And nothing about that is built in, right? We don't explicitly provide that route to the policy. It makes that decision on its own. So that's really an overview of the kind of results we have. So I'm going to next go into some observations, things that we learned from this that I think are interesting and worth taking away. But if you have some questions, this is also a good moment to cut in. Yes.
Are there any additional considerations to avoid collisions, or is it captured just through the reward function that it's like?
Just the reward function that says there's a penalty for colliding. And mostly it's even the penalty for colliding is very small. It's mostly that if you collide, you come to a stop. And if you come to a stop, you're never going to get to your goal. Daniel.
Is it, or the policy you sort of learn, is it that it can drive like a human driver, or is it that it can drive better?
It does not drive like a human driver. It drives well. Yeah, it's a policy that drives well. It is the first end-to-end planner we're aware of that drives really well in simulation and appears to be compatible as it can drive alongside human drivers.
And the reason I'm asking that because, okay, I think the fact that you can basically generate some data set on one end, and then you can do that without necessarily having to use human data.
Yep.
Make me think, okay, if I have a model, any model, not just a driving model, that I want to calibrate, right? It seems that there is a sort of connection between the two that could be had.
When you say a model that you could calibrate, what comes to mind for you? Yeah.
Or simulate it so that it replicates.
Yeah.
Real world.
Yeah. Yeah. You could definitely try to scale that up this way, if that's what you're thinking. Yeah. Yeah, for sure. Yes.
Because you have so many iterations and scenarios. How do you generate scenarios? Because I know you use Carta map, but map is just a map. How you design the obstacles and different traffic flow.
We don't. We randomly place goals all over the map, and we just let it flow after that.
But you definitely define something like the traffic rules or the size of the vehicles.
We randomly sample all of that. We randomly sample where the goals are. We randomly sample the reward functions. We randomly sample the size of the vehicles. It's just all procedural.
So So it's pretty harsh because some of the scenarios doesn't even show in the real world, but you still simulate that.
Yeah, we definitely have scenarios that are like 100% trucks, you know, for some reason. Yeah, but that's kind of the point. We want stuff that is weirder than the world. Yeah. Other questions? Yes.
Very quick specific question on this. Does the car know about the obstacle, even along with ride? So
Yeah,
it's
it has-
sort of assuming like very global perception.
We assume that you can see about 200 meters away. Not super crazy. When you're driving at high speed, you do have to see something like 150 meters, 200 meters away to drive safely. Yeah. So some observations I want to draw. The first, if you had told me before we did this that you could build something super robust with a 3 million parameter neural network, I would have been very surprised. This is a tiny, tiny neural network. We have a bit of equivariance, permutation equivariance. So basically each component of the state goes into a separate MLP. And then we apply a max pooling layer that flattens each of those components together. So it doesn't matter what order you pass them in. Not super important. And then that goes into a big MLP afterwards. But you know, in total, it's 3 million parameters, very small. If you think about something like ChatGPT, this is like 450 billion parameters. And if you even think about the prediction models that people use in self-driving, they will be easily, you know, tens or hundreds of millions of parameters just for the prediction module alone. And we've taken the prediction module and the planning module and flattened them together into one network. So there are no explicit predictions happening. I think this is extremely surprising. I find this weird. It kind of points to the fact that maybe planning actually isn't that hard, right? If it was very hard, I would think you would need a bigger function approximator to do it. Now, of course, like caveats, we haven't solved planning. I don't want to make the claim that we solved planning or anything like it. It's just surprising to me that you can plan this well with a policy this small. That is surprising. 2, you can fit many policies into one net. The single neural network is representing how you should drive if you're a pedestrian, a cyclist, a driver, a cautious driver, a risky driver, yada, yada, yada. All of that is activating different submodules of the network in some way that allows it to plausibly represent all of these things. Which also is very nice. It's very convenient because it means that we can do our entire simulator consists of one forward pass through the neural network to generate the behavior, and then one simulator update. Whereas when you have many policies all operating in the world, you have to sequentially iterate through them to compute what each policy is doing, right? So this actually is part of the reason we're able to be so efficient is it's all one neural network. 3, this is maybe an RL specific thing, but as far as we understand, and I also find this surprising, there is no wall. So when we condition the policy to drive safely, if we set up a simulation and we place all the cars in it and we condition the reward function to do safe driving, like say, don't be too risky, we can drive 1 million kilometers between collisions, which corresponds to roughly 17.5 years of continuous driving without a collision. Now, no one in that simulator is driving insanely risky, but I also, before we did this, did not think that a neural network could be that robust. As in, I thought you would need some kind of safety filter on top or some kind of explicit control barrier function or something like that to get that level of robustness. That's not to say that you shouldn't do that. You can place a control barrier function on top of this. You can add some kind of safety filter to modulate the action so that things behave more safely. But it is weird and surprising to me that you can at all set up a simulator with 150 agents driving around in it and they can go 1 million kilometers between colliding. I think that's surprising. Kind of ignore these 2 plots here. This is something specific to the little algorithmic trick that lived in there. If we abstract away from what happened here, what is this Gigaflow idea? It's 3 things. 1, it's some kind of goal-reaching game, right? We've set up a simulator, we've placed goals around the map, and we asked agents to just drive for 1 billion kilometers and try to learn to get to your goals without collision. 2, we have some kind of reward randomization that's generating the diversity in the simulator. And then 3, we have a scalable algorithm that lets us take all that data in and convert it into a reasonably good policy update in a way that seems to converge to something that looks like an equilibrium. If we abstract away from this, what does this look like? this is one, some kind of highly interactive task, in our case, goal reaching. Two, some mechanism of generating appropriately diverse partners. And three, some kind of scalable RL algorithm. And so you could try to fit a lot of things into this pipeline, right? You could think, okay, maybe I want to build really LLMs that know how to interact with their partner well. Well, the task there could be collaborative information discovery, right? Go on Wikipedia, you're a team of LLMs, find an article or a piece of information and bring it back to me as efficiently as possible. Your diversity could come from weak and strong LLMs, right? So LLMs with different levels of capabilities, so they have to reason about each other's capabilities. And then again, as always, it's scaled reinforcement learning as the algorithm. Or if you're thinking about robotics, you could think about human-robot task handoff as a source of interactive tasks. And again, in this case, randomized reward preferences is your source of diversity. You know, maybe preferences about how fast boxes are passed, how, you know, what hand you use, that type of thing. And then again, scaled reinforcement learning as a tool for bringing this all together. So some quick takeaways before I talk about future work. We've built the first simulated planner that zero-shot ACEs benchmarks. I think that claim is solid and holds up. I'm not aware of other work that has done this before. Two, there's not really a wall for end-to-end RL. You know, if you want to go to a trillion steps of agent experience, you can really continue to push agent performance up. It doesn't level off. Three, this idea of you can use large-scale self-play as pre-training, right? So you can just set up this world, drive around in it, and you learn some kind of fundamental skills that are repurposable and reusable for other tasks. I want to throw some limitations because for fear that I've been living on the hypey side of things, and I want to be put appropriate caveats into the things I've said. The first is this policy is not really all that human-like at all. To the sense that it is human-like, it doesn't collide all the time, which is not true for kind of supervised learning policies. But when we score it according to standard metrics for scoring human likeness, it's like 30th on the leaderboard or something like that. It's not very human-like. It's very pushy. It's very pushy. It drives, I think, I'm trying to remember, either a little faster or a little slower than humans tend to drive. So we lose a lot of points on that. Two, this policy doesn't have any history. So it does not condition on a history of states. It just conditions on your current state. And the only history we add, and this is critical, is you see how long other cars around you have been stopped for. And you need that because when you drive up to a stop sign, you need to know who has the priority order. So you need to know who got there first. It's not clear that it would have worked if we remove this limitation. So if we add history, things can actually go super awry, and we don't know what would happen if we had done that. So, for example, if you took my class, I have this example here where if you give agents access to blinkers in history, they can do this thing where they say, I turn my blinker on, off, on, off, on. That means I go first. You let me take a left. That kind of policy is extremely non-transferable to humans, right? That convention is not accessible to humans. This is called the cheap talk convention. Two, you know, I at the beginning of this talk, I kind of castigated spending a lot of time on designing complicated rewards that for your planner, but we also do have a lot of reward terms, right? We have about 10 reward terms that define the different ways we think the agent should drive, that kind of respect human preferences. What I do want to caveat though is even though we have all these reward terms and they look very complicated, I'm not going to go into them. None of these reward terms govern how agents should interact with each other. These are all convention reward terms. They're like, you should probably stay in your lane. You should probably stop at a stop sign. You should probably not drive at a 45-degree angle to your lane, right? None of it says though that like you should keep this distance from other cars. You should stop and let this guy pass. All the interaction between agents is not governed by the reward terms. Okay, and those are kind of the main limitations that I wanted to highlight. So what's next? So the first thing is this simulator is not going to be open sourced. It's not going to happen. I wish it would. But we've been doing a lot of work in the lab to build a better version of it. It's not there yet, but we've been building a simulator called GPU Drive that has all sorts of advantages over this prior simulator. The first is that prior simulator is written entirely in PyTorch. I don't know how much PyTorch you write, but basically to write that simulator in PyTorch, we had to solve a lot of tensor puzzles, like do all sorts of operations that PyTorch was not intended to do and make sure that they still vectorize. GPU Drive is built on top of a simulator called a framework called Madrona, and basically it lets us write C++ and compile it to CUDA. We don't have to do any tensor puzzling. Everything is vectorized for us. We currently have a policy coming out of GPU Drive that is collision-free in 99.1% of rollouts. So we're missing 5 nines after that 99, but we're getting there. It's coming along. 2, and I'll talk about this in a second, but one thing we've been doing, my student Stephanie Cornelise, is relaxing this constraint about not using any human data. You know, we've been trying to figure out how to fuse this type of approach with maybe half an hour of human data, or a couple hours of human data, or even thousands of hours, right? How do we get the best of both worlds without insisting that we don't use any human data at all? So we have a paper out in the Reinforcement Learning Conference about kind of removing the manual reward design of conventions and preferences that was in the Gigaflow work, where we kind of combine a term that is this kind of PPO reward, the RL term, with an additional penalty for straying from a supervised learning policy. So you like maximize the reward while making sure that you don't do anything too different from what a human would have done, given a bit of human data. Also, one other big kind of weakness of this work is, you know, we take our agents, we deploy them zero shot into a benchmark, and then they never get better. They don't learn anything from the fact that, you know, weird things happen in that benchmark and they don't match what they saw in their simulated world. So the Gigaflow driver is robust, not adaptive. So what we've been doing is trying to bring in ideas from meta learning to it, where basically you train with a pool of prospective partners, and then you get to play multiple episodes against those partners. And so over the course of those episodes, you can infer kind of how the partners prefer to play and adapt your behavior to match them. So 2 ideas about bringing human data in some way. So with that, I want to end with some acknowledgements, all the folks in the Apple paper, and this future work in GPU Drive. I want to mention Sam Kazankani, Ara Kanya, Kevin Joseph, Daphne Cornelise, folks who have been doing a lot of development on the simulator, and then Brennan Shacklet, who wrote the library that underlies that simulator. And here's the lab. Sometimes I'm missing photos of people. So if you're not on there, it's because you didn't send me a photo. So yeah. So with that, any questions?
We have some online if you can hear me.
Oh, there are questions online. Can we do in-person questions first?
Sure.
Yeah.
Close to human-like behavior. Can we prove that the simulation-like behavior is better than human-like behavior?
Yeah, great question. So it depends what your aim is, right? Oh, I'm gonna repeat the question is like, how important is it to match human-like behavior, right? Maybe that what's in the simulator is better than human-like behavior. Maybe that's the thing we want to deploy. It depends upon your aim. Sometimes the work we do in the group is about trying to build a human-like behavior so that we can use it as a way to measure safety, right? So we could set up some intersection, do 1 million rollouts in it, and see how many collisions happen, right? And the aim is to match human behavior. If you're designing an autonomous vehicle, maybe you don't care all that much about matching human behavior. You kind of want to match it a little bit, because if you stray too far, you know, there could be unexpected side effects and weird things could happen in edge cases. But, you know, humans are not great drivers. You know, we crash every 20 to 100,000 miles. We have a fatality every 100 million miles, something like that. We can do better than that, and maybe not matching human behavior is the way you get there. Yeah, great question. Ishwan and yeah, so I like these like mixed losses. So like mixing between RL and imitation learning, like we did in that paper. We've been looking at scaling that up. You could imagine fine-tuning a supervised policy. You could imagine having a human behavioral prior that you just like pick from. So the human thing gives you trajectories and the RL policy picks over them with a cost for switching. There's a lot of things I don't think we know. I think the right thing is to mix these 2 things together. But I don't think we know what the right approach is.
I didn't understand what was the advantage of using self-play, like if we don't use it, what would be the other options and what is the advantage of?
I think there really are only a couple other options. One option is scaling up human data collection. B is like kind of hand designed planners, like, you know, you kind of write down the whole planning stack yourself in some way. And then C is like kind of the self-place type thing. It's just, it's the only way I see to generate tons of synthetic training data. Like the synthetic training data needs to come from somewhere. Where does it come from? It has to come from rolling something out. Yeah.
So the talk really exciting. So this Gigaflow, there are two elements which are better. First, you showed that benchmark, it was, you know, better. The second, you also mentioned that 3 million parameters is a smaller model than what happened on average. Did you seek that out to kind of make it as kind of parsimonious as possible, or was that just that came out as a nice thing on the side?
Why is our model as so small is the rough question? Like, is that something we seeked out? So there's a couple answers to that question. The first is there's a size trade-off. So as I make my model bigger, the forwards pass of my rollouts becomes slower and slower, right? So by making the model bigger, I have a higher capacity model. I can fit more complicated policies into it, but also I get less training experience because rolling out the simulator becomes more expensive, right? Because I have to inference the model every time I roll out the simulator at every step. So somewhere there's a sliding scale between capacity of the model and how much experience you can squish into the model. And we wound up somewhere on the spectrum. We definitely tried training bigger models, and things got worse. So like maybe above that, sliding scale wise, we were better off getting more experience and having a lower capacity model.
So if I understand it correctly, for a certain compute, this is the size.
Yeah, this might be compute optimal. I'm not going to claim that it's compute optimal. It definitively is not, but like we were not able to find a more compute optimal setting around where we searched. The other thing is, you know, if you can fit such a complex policy into this little thing, then maybe we don't need that extra capacity from the bigger model. We're not getting it from it. So, you know, maybe this is a good size.
Compute wasn't a constraint. We would have gone with a bigger model, or
No, our results got worse when we had a bigger model. Yeah, I mean, RL has this complicated thing where sometimes bigger models do worse, genuinely, even for the same compute for the equivalent size compute budget. A little unclear why. Right? It's still an active topic of debate in the community. It's a good question. Yeah, sorry. To repeat, the question was, would we have gone bigger if we had more compute? We weren't super compute limited, so yeah. I think there are questions in the chat, I guess.
Yep. I can
don't
read them too if you
see
want.
questions in the chat. Oh, here it is, Q&A.
Got it?
Okay, how are the input from these data sets, Carla Waymo, the same to the input from Gigaflow? We write a little wrapper layer that maps the inputs to match those from Gigaflow. Are the inputs about road boundary stop lines easily available in the real world? The inputs that we take in are roughly what any sense stack for an autonomous vehicle will be able to give you. They have to see the cars around them. They have to know where the edges of the road are, those type of things. Are there any plans to release the source code? I'm not at Apple, so I do not know the answer to that question, but I would bet that the answer is no. Hey, Cameron. Given self-play, how do vehicles learn to drive on the right side of the road? So two things. One, there is a reward term that says be aligned with your lane. So we know what the heading of the lane is, and we reward the agents for being in that. We also have the opposite of that reward term. So some agents want to drive in the wrong lane. The other thing I'm going to add is that to make things match to work in Singapore, we actually take each map and we mirror it. So we actually train on 16 maps so that all the maps mirrored, and that lets us drive in Singapore. Are there any plans to release the GPU infra source code your team is building? Yes, it's open source. So you can just go on our lab GitHub or search GPU drive. It's all there. And it's under an MIT license, so anyone can use it. Was there any effort at Apple to make this run on a real AV? I am not going to answer that question. No comment. Okay. Anyone else? All right, well, thank you all very much for your time.